Okay, welcome to fancy Newport Beach, where everyone has a car, kind of like Will Smith. $100,000 cars, everybody got them. But here I am with a Mazda 3, and my Mazda 3, it's really not a Mazda 3, but it's a Mazda, and it's worth more than every other fancy car within a quarter of a mile combined, because this is a prototype. So Coleman's going to talk to you about some of the technical stuff, and you and I are going to talk through some driving. So let's put our foot into this thing.
So MotoMan said he didn't understand anything that was going on here and I should explain it for him. So here it is. This is the new Mazda SkyActiv-X engine that we're working on. It is a spark controlled compression ignition engine, which is kind of a whole new thing. What we're doing here is trying to figure out how to burn a lot less fuel and make the same power. We run lean compression ignition. What normally in the spark ignition gasoline engine you run air fuel ratio of lambda 1 or 14.7 to 1 if you're talking in mass. That's the exact amount of oxygen that you need to burn the amount of fuel that you're putting in there. This engine runs extremely lean. You'll have 2 to 3 times as much air as fuel. And the reason that's helpful is that the fuel that burns will then, instead of dumping all that heat into the engine and heating up the engine and wasting energy there, that heat gets dumped into that extra air. That extra air then expands and pushes on the piston even more, so you get more energy out of it when it's really lean. The way that the air absorbs that combustion heat also lowers the combustion temperature, which reduces NOx emissions as well. So it's a really good thing to do. It's really difficult to pull off. You can't get flame front to travel from a spark plug out through the whole cylinder when it's that lean. The fire just kind of peters out. So what we do instead is we compress it a whole lot more, and at really high compression we can get to a different kind of combustion where it spontaneously ignites instead of just burning from the spark plug. And this is what is conventionally called HCCI, or homogeneous charge compression ignition. HCCI in its pure form is really hard to control because you don't know when the combustion is going to happen. You just compress it all, and sometime when it gets to the right conditions, kablam! And if the piston's still going up, well, bad news for you. Or if the piston's halfway down, well, you just wasted some energy. So what we do with spark-controlled compression ignition is we compress the air-fuel mixture up to almost the point where it's going to go on its own, to just below that. We set up the engine so that it will never quite go into HCCI. And then we fire the spark plug, and that little bit of flame kernels that happens from that spark plug will compress and heat the air-fuel mixture just enough to push it over that edge, and boom, then it goes into its spontaneous compression ignition at that point. That's something we can control the timing of, and that's what we're doing in this engine. Now, that's a really sort of simple explanation of what's going on. To make it happen in a car that you can drive every day and can feel totally normal is actually really complicated, and it ends up kind of turning a lot of things on their head in the way we designed this engine. This engine is put together with a lot of familiar parts. Kind of every component in this engine is something that exists somewhere in the automotive industry, in some other engine somewhere, but the way we've put it together and what we're doing with it is completely new and unique and different. So if you're familiar with what an engine should look like and you look closely at this, your head's going to explode because everything is wrong, everything's backwards, everything's in a weird place. So I can just kind of walk through this and sort of try to explain what is where and why those things are in the places that they are. So first of all, on top you see this big shiny thing. This is the fuel injection system. This looks very much like a diesel fuel injection system. It's a little bit lower pressure than diesel, a little higher pressure than a conventional direct injection system. Normally on a gas engine, the direct injection, the injectors would be in the side and the spark plugs would be in the middle. And the reason for that is you want the flame path from the spark plug to the end of the combustion chamber to be as short as possible. Well, we're not doing that flame path anymore. We're burning everywhere spontaneously all at once with compression ignition. So now we put the injector in the center so we can control the fuel distribution in the cylinder as precisely as possible. And we put the spark plugs over here on the side because we don't really care nearly as much about where they are. So this, in that sense, kind of looks like an old 70s engine where the spark plugs used to be on the side. If you look at the front here, we have a supercharger on here, which that seems strange, right? We're trying to run a lean air-fuel mixture all the time. So what that means is that as we start going to higher load and trying to make more power, it's a 2-liter engine, and a 2-liter engine is only drawing in so much air. So as we put in enough fuel to get to maximum load, it's not lean anymore. We don't have enough air to keep it lean. So we use what we call a lean supercharger to pump in additional air and keep it lean all the way to maximum load. So physically, this is a roots blower like you would have on a supercharged engine, but the way we're using it is not the same. We're not. If we were doing a power boosting with this, we would spin it faster, put a bunch of extra air in there, and then match it with the same amount of fuel. But since we're keeping the fuel lean and running in this compression ignition mode, the sort of purpose and the result is very different. It's pretty good power and spectacular efficiency is what we're going for here. Now, the way the supercharger is laid out is a little bit unusual too. Because we only use it at high load when we can't get enough air naturally, it has a clutch on the front of it. So we turn it off at low load, at high load we turn it on. On the back here we have the throttle body where the air is drawn into the engine. Most of the time actually, even at light load, the throttle's wide open because we're trying to get as much air in there as possible. We just use a little bit of throttle trimming to sometimes control how things flow when we're mixing exhaust gas in. We have an EGR system where we can mix in a whole bunch of cooled exhaust gas to mix in with our air. Because what we want with this lean mixture is to have as much air volume in there to buffer that combustion and to take that combustion heat and turn it into pressure. We don't necessarily need all the oxygen all the time. So sometimes we'd rather have the used up gas that came out of the exhaust. So we have a big EGR cooler on the back here, EGR valve. We can mix those two gases together coming into the supercharger. The other thing we see here is a bypass valve for the supercharger. So at light load, we don't go through the supercharger, we go through this bypass valve through this little hose and into the engine. When we turn the supercharger on, we can kind of throttle this valve and adjust how much boost it's making at that point. The air that goes to the supercharger comes out the front here, goes down through this funny looking box, which is just a rectangular hose really, and goes into this air to water intercooler. So we can regulate the temperature that's going into the engine. And then tucked up underneath there where you can't see it is the passage that goes back up into the intake manifold. So that's sort of the airflow path there. One thing you'll notice is you're looking at the front of the engine here, there's no timing chain, there's no cam gears. Those are on the back. That has nothing to do with it being HCCI necessarily or SPCCI. It just has to do with how completely out of the box we're thinking with laying out the engine. We put the timing chain on the back of the engine. One of the advantages of that is it makes all the timing, the noise from the timing chain is a lot easier to isolate. It's mostly going into the bell housing, into the transmission. It also packages a little bit better. We have more room for the actuators over here. Now on the back of the engine you have two variable valve timing actuators that are both electric. SkyActiv-G engine has electric variable valve timing on the intake, but hydraulic on the exhaust. In this case, we need really fast timing changes on both sides. We can switch into sort of a Miller cycle mode where we're throwing out some of our compression and pushing it back out into the intake, or we can run full compression. We can do all kinds of different things here. One of the reasons we need this really fast valve timing is that at some load conditions we can't achieve that lean compression ignition, and we have to switch back to a spark ignition mode. Well, we've optimized this whole engine around lean compression ignition. It has 16-to-1 compression and a supercharger on it. If you do conventional spark ignition in those conditions, the engine can't handle that. That's a combination that just won't work. So we can switch over to spark ignition and use the cam timing to effectively throw away some of our compression, run it as a Miller cycle at those times, and then we can operate safely in that range. So there's a whole lot of stuff going on here. The other thing you'll see on the belt drive on the front, the alternator has this really crazy tensioner around it. That's because this alternator is part of a mild hybrid system that can actually start the engine. We can drive the alternator, drive the belt the other way and do a start-stop with it. So if you're familiar with the IE loop system that we've used previously, where we'll take the alternator load, dump it into a giant capacitor, and then turn off the alternator when we're driving the car and just run the electrical system off that capacitor. This is sort of an extension of that system that's more capable, has more storage, and is able to do more things like drive the belt system backwards. I think I just said everything I know about this engine in one shot. There's absolutely nothing else unconventional about this engine. Now actually, an important point, because MotoMan, as his head was exploding, when we were explaining all this stuff to him, he just couldn't get his head around how can all this new crazy stuff be reliable. And I don't have a simple explanation other than that, you know, we're really good engineers and we're testing the hell out of this thing, and we'll have a sort of don't worry about it. But as new as the concept of what we're doing here is, the way we're executing it is with a lot of parts that are proven in other engines. So like ignition coils, spark plugs, fuel injection systems, superchargers, EGR valves, all these things we know how to make. We've been making in lots of engines. We just put them together in an unusual way to achieve a different goal. So you know, that on top of our development process, we really have no worries on our end about the reliability of this engine. This should really be a rock solid performer. We've got another year to year and a half before we go into production too. So we've got a lot of testing yet to do.
Okay, past the Jetta. Let's get past the Ram and the Roach Coach. Put our foot into this. Foot to the floor. Okay, we got about a half mile before we switch freeways, so let's try this again. Accelerate. Try to get around the Prius so we don't sit behind him on the exit ramp. And what's surprising is there is more pulling power. It's noticeable over a current 3, even though this one's designed to run more efficiently through what Dave is telling you guys about a leaner setup and a higher compression ratio. At the end of the day, it does feel a little bit more lively than the 3 that you and I have driven, God, what, 4 or 5 years ago? But keep in mind, I drove a regular 3, so not this, a regular 3 from the hotel this morning to Mazda in Irvine. And it was kind of a reminder, it's like, it's the best car that you always forget how good it is until you drive it. And then it's kind of back to back, and I'm thinking that the PR folks did this by design to make you have like a back-to-back experience of the difference between SkyActiv and SkyActiv-X.
All right, MotoMan was just telling me how he was so incredibly comfortable and confident and in control and really enjoying driving the car, and he wanted me to explain why he felt so good. So this is me attempting to explain why he's such a happy guy. He was driving our prototype of our 7th generation platform, and the platform looks relatively conventional. It's got 4 wheels, steering wheel, that kind of thing. What's kind of unique about this is our approach to tuning it and where we were focusing our energy. We've got this philosophy called Jinbai Itai, which is Japanese for horse and rider as one, which means nothing unless you like riding horses. But really what it means is that we're focused on the interaction between the driver and the car and making sure that's as natural as possible so that you really feel at one with the car. We're not that worried about 0 to 60 times or cornering G or any of that. That stuff will sort itself out. If the driver is happy and feels like they're in control, that's what we're really after. So the way we went about trying to achieve that on this car was really studying what the people in the car are needing to do continuously, subconsciously when they're riding in a car, and that's simply dealing with G-forces. A caveman did not have to deal with the kind of G-forces that we're dealing with in the car. They weren't sitting on things that moved around, right? Our internal systems are made for only one activity that we have to balance against, and that's walking or running. So if we study how people walk, that will tell us how we should make the car move. And if you look at when people are walking, basically you have an upper body from the pelvis up that's riding as a passenger on this elaborate suspension system here. So we looked at trying to make it so that the person in the car can have their upper body in a basically similar position to when they're walking, and that the car's behavior can mimic what your legs are doing in terms of what inputs it's putting into the body. So we made the seat support your upper body in a very much sort of walking posture, so your back has that same sort of S-shaped curve that you have when you're standing. And then we tried to tune the car so that the inputs match the way humans move. So there's this area of study in human biomechanics it's called minimum jerk theory. I don't think it's a human thing. I think it's a mammal thing. But minimum jerk theory is just saying that MotoMan's not really that much of a jerk. No, it's got nothing to do with that. It's got, jerk is the rate of change of acceleration. So what it means is that when people move, they accelerate and decelerate their body as smoothly as possible. That's simply how we evolved, because it uses less energy. We don't have to eat as much food if we do that. And so that sort of informs how we should make the car. When the car goes over a bump, we want it to move over that bump very smoothly, accelerate and decelerate as smoothly as possible. And that seems like an obvious thing, but previously when we were designing a suspension, we were really focusing on the amount of energy that's transferred from the ground to the person, because you're dealing with all these different kinds of inputs that you can't predict, and looking at it from a sort of an energy viewpoint was kind of the most efficient way to do it. But what we found is that if we tuned the suspension system, and when I say suspension system, I mean every single part between the tire and the driver. I'm including the body, I'm including the seat, I'm including the suspension, I'm including the tires. If we tune that to all work together harmoniously to deliver this smooth input that's similar to the way you're moved when you're walking, people were not only more comfortable, but we could make the car stiffer and firmer and have more damping and more control, and actually have bigger inputs coming into the car and not have people be uncomfortable. They were much, felt like the inputs were more natural, smoother, and cleaner. So there's a ton of detailed changes to the way we tune this car that all of them individually seem pretty insignificant. Oh, we made the sidewall softer. Oh, we made the bushing stiffer. None of that really seems to matter. What matters is the way that all goes together as a whole to make this smooth, natural motion that made MotoMan so incredibly happy. Like I said, it looks conventional. There's only one unconventional thing on here that I can actually point to and say, hey, look at this new thing. And that is this damping medium that we've built into the body structure itself. So we want the body to be as stiff as possible, to transfer motion from the wheel to the seat as quickly and cleanly as possible. But we also want to filter out any vibrations, because that's something that your legs aren't delivering to your upper body. That doesn't feel natural. And we figured out that we can actually build these damping nodes into the body. And there's one right underneath the seat mount rail here. Boy, this would be a lot easier if I had like a piece of paper to bend or something like that. So if we have a rectangular cross section and it can kind of bend in a parallelogram. Is that a parallelogram? That's a parallelogram like that. We can put like a shear plate in that panel, and that would make it a lot stronger. What we do instead is we put a shear plate in there and we connect it on 3 sides and leave the last side disconnected. So when that thing's deflecting, that shear panel and the floor are moving right next to each other in opposite directions. And then we put this this piece of damping material. It's a bonded mystery material, really. There's some bonding glue and some sort of resin that glues those together, but damps the frequency ranges that we see in the body structure. And we're able to actually sort of focus the vibrations in the body into these little pads, and then damp out the vibrations. So we put some of those right underneath the seats. We put them in all together about 12 different places in the body. There's places where vibrations are coming from different directions and crossing, like right in here, for example. And if we put some damping nodes right in here, we can sort of cut out some things right at the intersection and smooth them out. So that, in a really big, convoluted, clumsy nutshell, is why MotoMan was so happy.
Okay, being that we're in Orange County, this is probably the only turn we'll get straight here, so let's get off the freeway, go on to Baker Street, try to get some around town to feel the difference in some of the structure. Now, Dave just told you a ton of the changes, down to some sort of a node in the way the joints are built or really connected on this car. So let's come around this a little fast, and please don't try this at home. That's about the sharpest turn we're going to get here. So it's not entirely fair to Coleman to judge driving dynamics around these arrow straight roads, but let's do a little bit of elevation change, put our foot into this thing and do a quick lane change. I can't say I notice a huge difference between this and the current 3. I think we're going to have to put a pin in this, come back to it, because remember the CX-5? That was a lot of small changes that added up to one big change. This, it isn't tuned yet. He still needs to tune it for us to make a determination on this thing. As we get back into town here, a little bit more traffic, a couple of notes. Number one, the brakes are different, but not calibrated or finely tuned. The transmission's Not really different, but it's been calibrated differently for this engine. Again, we have to do a pass on this one until we see the final vehicle. And then one thing I've noticed is let's come around this turn here and go off on this side street. And because this thing is really lean and the compression ratio is really high, you do hear a knock every once in a while, being that this is a prototype vehicle, which is interesting to hear, especially at like low speeds. Let's try to see if we can get it here. Oh, there's the knock. You can hear it as we get behind the Mazda 6. I don't know if Coleman has littered the road with Mazdas or it's just a natural thing here in Irvine, but there's a lot of Mazdas down here.
MotoMan wanted to take a shot of this car that's a slightly different shade of silver, so he wanted me to say something else. I told him I've already said everything I know, so I'm struggling here. But I didn't talk much about the seat yet, and the seat's a really pretty amazing part of the suspension system here. We've really tried to stiffen it up and have a lot more damping in it, so it feels really, the inputs you get are really clean and well damped. One of the things we did to make it stiffer, of course, is more ball bearings, because it's all ball bearings these days. The seat sliders, our old sliders would have two ball bearings controlling the upper and lower parts that are sliding. We now have 4 ball bearings up in the corners, because when you bounce back and forth in the seat, you're kind of pulling the upper and lower part of the slider apart, and putting bearings up in the corners makes it a lot stiffer, and so you don't have that deflection in the seat. That is exactly the kind of detail I'm sure you really, really wanted to know about this car. MotoMan wanted to ask a silly question about if we should apply this technology to a rotary. I'll tell you right now it's impossible, but he wants you to convince me that it is possible somehow in the comments, and something about social. I don't know how this internet thing works, but you know what to do.
So as we get back to Mazda here, a little bit behind the scenes, number 1, you got a A319 Delta landing at Orange County Airport. And number 2, I am not alone. You can't see it, but there's George next to me. He's an engineer here at Mazda. George and I started chatting. It turns out not only does he have a great name, George, but what school did you go to, George?
Arizona State.
So does that mean you're a proud Arizona State Sun Devil?
Absolutely.
Okay, everybody say thank you, George, for engineering this car for me. And because you're a Sun Devil, we like you better than Coleman. Yes, I said that, Coleman. He's better than you because he's a Sun Devil.